Welcome, everyone. This is the Resonance Academy, and you're here with me, faculty member Adam Apollo, and we are going to be exploring the quantum geometry course. This is your free course intro session, and for those of you who have not registered for the course, you can do so at any time at bit.ly/quantum-geometry, or you can go through the Resonance Academy site or the main Resonance site, and then access course electives, and you'll find the quantum geometry course there. For those of you that have already decided to join me on this adventure, thank you so much. It's really an honor and pleasure to have you here. We are going to do some epic deep dives into the nature of reality and space-time and physics and consciousness and everything else. And so this course is really the output of many years of work on my part, and the accumulation, as those of you know that have been on a lot of the Resonance Academy expeditions and adventures, many different pieces that I've been assembling for a long time have finally come together and shaped this very clear and simple and pure expression of my perspective in unified physics. So I see a lot of you guys popping up in the chat here and saying hi from different places. We've got people from France and Mexico and Canada, Brazil, San Diego, Asheville, North Carolina. What's up, Asheville? Copenhagen, Virginia, Toronto, Huntington Beach. Thank you guys so much for joining me. Please, if you haven't said hi in the chat, please do so. All of you are welcome to at any time post questions in the Q&A. Or post questions in the chat, although it's a little easier for me to track if you use the Q&A button at the bottom of the Zoom, because the chat sometimes just gets going and people posting and sharing and responding, and I'm looking over here, not over there generally. So what is this course? What is quantum geometry, the unified physics of the proton and the quantum mechanics of space-time? For me, creating this course has been about really getting to know what the structure of space is and how it works and how it operates. And from a lot of the very fundamental principles that I discovered around the nature of space-time and my own theoretical approaches to it all the way back in 1998 to 1999, and in the year 2000, when I produced my first paper called The Unification of Science and Spirituality Through Unified Field Theoretics. The evolution has been to test and apply and look at experiments and look at actual data in atoms and molecules and get a deeper understanding of how this fundamental field dynamic actually generates the forces and the matter that we see all around us. Everything from the perspective of unified physics comes from the structure of space-time. So we're hearkening back to the original perspective that came through actually many philosophers, visionaries, thousands, for thousands of years, that there is this kind of underlying field, and that underlying field, which the Greeks called the ether, which the Taoists called qi, or in China is called qi, which in Japanese is called ki, or in ancient India was called prana, and has several different names in different Native American traditions, and South American traditions. It has other names depending on the tribe. And this sort of vital force, or odic force, as you'd find in the Nordic cultures, was always seen to be this fundamental, this ground state through which all the different elements in general arose. And we have depictions of these different elements in different cultures. Fire, air, earth, water is generally the four that are across most cultures on the planet. And even today, we look at our approaches to different fields in science through the lens of the study of thermal energy, In other words, the study of plasmas. We look at the study of solids, liquids, and gases. And these four states of matter really form the foundation of our studies in physics. And really, we are just looking again at the four elements. We're just calling them a different thing. And so I began to really look at what is the insights that we can glean about the nature of this fundamental field. And I dove into research and work studying different scientists and different leading edge thinkers at the time as I was in my latter years of high school. And through the work of Brian Greene and Lee Smolin and loop quantum gravity, and Roger Penrose and many other amazing thinkers, I started to get the picture that there already was a huge amount of work done to look at the quantum mechanical structure of space itself. And I began to realize that that in every one of these theories that were highly successful in defining equations that could actually describe what a quantum gravitational theory might look like. In other words, something that could take our understanding of gravity, the curvature of space, the field that attracts planets and planets to stars, um, and apply that to looking at the microcosmic world, how atoms come together and protons, and what's going on in the quantum mechanical fields of the smallest things in the universe. And and so all of the most successful ones described space-time as a discrete structure. And this structure that was proposed was seen that it would make the most sense that this sort of baseline structural field would occur at the Planck scale. And many of you that have taken other courses in the Resonance Academy have come to know a lot about the Planck scale, and gotten to know some of the work of Max Planck and his work in unifying our perspective in different forces and energies, from Planck time to Planck length to the Planck energy, and seeing that there is a sort of universal crossing point between all of these different studies of reality. And for our purposes, understanding that at the Planck scale, there is a structural lattice that forms spacetime is really important. Now, of course, in the work of loop quantum gravity, Lee Smolin and others, and we'll do some review of this in the course, um, they had a very hard time seeing what the geometry of this sort of structural lattice that's forming spacetime could look like. Usually have these like long triangles and short triangles and squares and these gaps and all of these things. And the way that they were modeling this was described more as like a quantum foam, this bubbly matrix of energy that's and that has very little order and very little structure to it, and so gives rise to these very strange, odd probability dynamics in quantum mechanics. And when I saw that, I immediately felt like something was significantly wrong with that approach, and that there needed to be, in a sense, a better structure to this fundamental field. And the more I dove into the energy of the vacuum by, exploring vacuum energy itself, by exploring Einstein's equations, and realizing that the vacuum itself, this empty space between things, should be full of all kinds of energy. This was long before I met Nassim. I started thinking, well, there's got to be a way that this energy is there and is not showing up everywhere. And I thought, well, what way could there be a huge amount of energy in this supposedly empty space and we not notice it? That we not actually see it in the experimentations, that we not actually come into contact with it all the time. And that's when I started thinking about equilibrium. And I started noticing that anytime you have triangular structures, especially equilateral triangles, you can have a huge amount of energy or pressure on any one of the points of the triangle. And yet the triangle will retain its structure and its shape. And you can even put more pressure on one side or another side, and the triangle will still maintain its shape and solidity. And I started thinking about not only the triangle, but the tetrahedron and pressure on the tetrahedron. And somewhere in there, I came across Buckminster Fuller's work. This would be in the very late 90s or early 2000. And I found that Buckminster Fuller, as this amazing thinker and inventor, um, that he had really broken down and taken a look at all the parts of the way that triangular equilibrium structures can fit together and move and shape themselves. And that the triangle in itself, when you have a state of total equilibrium and you spread a triangular lattice across any surface plane, you get perfect hexagonal geometries, honeycombs, if you will. And these hexagonal geometries form this sort of flat space where all the tension is equal in every direction within that surface. If you apply it three-dimensionally, you end up with this tetrahedral lattice where all the structures are tetrahedral to each other. And again, all the pressure, all the energy is equalized in every direction and extremely balanced. And I thought, well, that's perfect. There you have it. There is this equilibrium structure underlying this sort of tension in space-time. And Buckminster Fuller introduced this idea of tensegrity to me through his writings, of course, and perhaps a few dreams and things like that as well. And tensegrity, as I began to explore it, really embodied the essence of how a push and a pull can be equalized. So imagine now that you have this tetrahedral lattice of nodes, and each one is vibrating and radiating out. So it's pushing against all the other nodes in the lattice. But at the same time, there is a charge attraction. And this charge attraction, due to spin, torsion of the field, rotation of electromagnetism at the smallest wavelengths at the Planck scale, we don't know. But that attractive charge is also pulling equally all of those different essences together. So they have this push and pull that's equalized in the structure of the fabric, which makes it, frankly, highly crystalline and highly solid, because it's the same exact balance of push and pull between different molecules in a crystal that give a crystal its clarity and shape and the lattice work that makes it clear and beautiful and perhaps colored, and allows it to be extremely hard and very solid, but also have very interesting electromagnetic properties. Piezoelectricity, for example, is a quality of many crystals where when you simply press tension on the structure of the crystal releases electricity. And in some cases, there are even a lot of proofs where people put pressure on crystals and light or photons are emitted, and not just electron charge. And so the technology of this sort of squeezing crystals in little ways to produce charge and light is actually the foundation for things like liquid crystal displays, LCDs, which many of us experienced in our first cell phone or in our early calculators that we were using. And crystal displays and the act of squeezing a crystal to produce a frequency or charge we see in technologies everywhere. And so now let's look at space-time as this crystal that when squeezed just the right way propagates charge. In other words, the whole thing is in this state of tensegrity and balance with itself in this crystalline structure, and yet it's vibrating. And whenever there's a wave that passes through it, that wave will continue propagating through it at a very high speed. And the speed at which the waves can propagate, the actual charge waves can propagate through this lattice, moving Planck to Planck to Planck to Planck, is the speed of light. And the speed of light actually sets this sort of limit, and it's just a limit of charge propagation through this matrix. Now, there are some different considerations to take into account. When we look at Einstein's work, we realize that light movement is always relative to the observer, that things like time dilation occur when we approach the speed of light. There's a lot of interesting concepts here. And while I'm not going to cover all of them in this intro session, I want to give you guys a really good foundation for the material that you're going to explore in the course. Because inside this course, I actually unpack this a lot deeper, and we're going to apply a lot of these relativity dynamics to understanding the proton itself and how it's spinning in the field of spacetime. So to start with, let's just look at relativity and general relativity in the way that they combine as we look at the structure of spacetime itself. First, we know that light traveling, propagating in waves through this lattice that is this Planck spherical unit entangled crystalline structure that's spacetime itself, that light will curve when the space-time structure itself curves. And so this was originally an idea called the luminiferous ether, that there was some kind of fundamental underlying essence that would control or affect the movement of light. But in Einstein's special relativity, he didn't use the underlying fabric to describe light's movement and to describe the relativity of light and time. And so people were like, oh, great, we don't need the ether anymore. However, as I present in a lot of my other work, Einstein, only a few years later, produces general relativity. And general relativity describes space-time as a structure, as a continuum, and that continuum affects the flow of light through it. So when that continuum bends, such as in a gravitational field around a planet or a star, the light is going to follow the flow of that pattern in space-time. And as it follows it and moves with that space-time, the light will curve. And we've seen this experimentally many, many times. We call it gravitational lensing. In fact, when it's so powerful that a distant galaxy is actually bending the light of galaxies behind it around it. So we actually see multiple copies of the same galaxy around a galaxy where the light from that galaxy's been bent. And so this is not just theoretical, this is direct experimentation. We know that space-time acts like a lens for light. And this is a really important concept, but it's one that comes up really hard against this idea that space-time is always this state of equilibrium and in this kind of even tetrahedral matrix. And I knew that there was an issue with that right from the beginning. And I started thinking about what the geometry would look like to be able to create curvature in space-time. And Buckminster Fuller really gave me the tip and helped me out because he showed me initially that if you take 6 equilateral triangles and you remove one of them, the other 5 will bend together and they'll form a perfect pentagon, and it'll be a pentagonal pyramid. And that pentagonal pyramid will begin curvature. In other words, it will flux the rest of the field and pressure it into turning a little bit. Now, when I was in college, I got to really play with this idea, and I experimented with creating my own pentagonal curvature field through a hexagonal lattice. And to do that, and you can do this at home, and I highly recommend doing it because it's a great thought experiment. You just take a flat poster board and you draw straight lines across it and you evenly space them, maybe an inch between them if you want. An inch is pretty good. If you do 2 to 3 inches, you're going to get a pretty big structure. And so you're going to do parallel lines, let's say an inch apart. And then you're going to basically triangulate those lines. So you just draw a circle, and then you pick one of the circle intersections with the line and draw another circle. And you pick an intersection between the 2 circles and you draw another one, and you just make a little flower of life. And that will give you all the points you need to then triangulate the lines across the board. So you end up with a board full of triangles. Now, if you're, as obsessive in your drawings as Robert Grant is, and you really want to do it as a mental exercise to reveal the deeper gifts in the structure, you can flower of life the entire thing if you want. Now what you do is you're going to basically cut portions of that poster board so that you can take one of the triangles out of any of the little hexes that you've chosen. And you're going to bend the poster board or slice it so that you can bend it to form a little pentagonal pyramid. And then you just continue all the way around. You keep folding pentagonally, and what you end up with is a perfect icosahedron. And it's quite a beautiful thing to see this flat surface curve, but the mediator of that curvature is the pentagon. And it's really important that we acknowledge and we recognize that, because the pentagon or pentagram has been a massive sacred symbol across many, many cultures all over the world for thousands of years. And we wonder, like, where do these sacred symbols come from? Why would a culture apply this idea to a geometry that it has something to do with their relationship with creation, their relationship with gods and goddesses, their relationship with source, their relationship with elementals, however you want to look at it? And I think the answer begins to be revealed as we look at these geometric dynamics in space-time itself. And we begin to see that without the pentagram, without the pentagon, you don't have curvature of space. And if you don't have curvature of space, you don't get gravity, because gravitation is just space-time and curvature. And if you don't have gravitation or curvature, then you certainly can't get matter. And if you don't have matter, then you don't have any experience of the physical world at all. And so perhaps this idea that the pentagram is connected to our relationship with the essence of creation in the physical world is deeply oriented and related to um, our consciousness of the physical world, and is related to the nature of curvature and mass itself. So the actual geometry that creates mass and curvature gives rise to this experience of physicality. Now, I immediately, upon meeting Nassim and exploring his work and seeing what he was doing with the flower of life structure and seeing what he was doing with the tree of life structure, I immediately saw that he was really missing this really critical piece. And this piece is about the pentagonal curvature. And I realized, okay, I'm going to have to really do my work around this, because I need people to understand this curvature system. And I need people to understand that this is the fundamental structure that allows curvature in a highly energetic crystalline structure of tensegrity that is what we propose space-time to be. And Nassim and I's, theories and ideas have aligned more and more. And now, of course, he speaks a lot about geodesics. And geodesics are simply spheres or spherical structures in which there is a mediation of the curvature through positioning different pentagrams inside of that field. And as you'll see in the course, I often will render the proton and the layers of the proton as the very, very innermost layers, where you can actually see the pentagonal intersections. And there are 12 of them, which 12 is also the number of the vector equilibrium. 12 vectors in equilibrium give us total balance in space-time. So even with these spheres, they're still in their own state of balance and equilibrium. But as we look at these kind of internal structures to the proton, it's important to remember that the layers go on and on and on and on and on and on and on. And as Nassim has so astutely observed, the actual Planck scale structure where these pentagrams exist, going out to the full structure of the proton, is like a single grain of sand as a Planck spherical unit to the distance between here and Alpha Centauri as the radius of the proton. So there is a huge difference between the little geometric structures and the massive structure that actually is the full proton. But for the sake of rendering inside my course, I'm generally showing you what's going on closer to the core in the proton, so you can actually see these points of curvature, because understanding those points of curvature help us to see the tension that's created. And that tension continues to grow and grow and grow and grow the further apart these little 5-pointed lattices are. And as you go out in the proton all the way to the surface, the tension lines are massive between the polar points and these upper hemispheric points, lower hemispheric points, and the bottom point. And that massive tension is what's holding that event horizon together as the proton is spinning at the speed of light around its equator, shearing the fabric of space-time. In other words, mass dilating itself so much that at its equator, it behaves as if it has no mass. And this is something that we're going to unpack a lot more too, because this is related to Einstein's theories of time and light and movement in space. One of the things that Einstein showed us is that an object that's moving at the speed of light does not experience time. And so if you're going at light speed, no time is passing for you. And the curvature of time dilation, as you go from relatively zero to relatively close to the speed of light, is such that everything in the universe changes in relative time dynamic to you. So, for example, if I were to accelerate, and this is the really key word here, if I were to accelerate towards another star, like traveling to, let's say, the Sirian star system around, 4 light years away, and I'm going and I accelerate up to nearly the speed of light, I'm going to experience the travel to that star and back. And let's say it's 5 light years away. I'm going to experience that within, let's say, 5 minutes. Because in my experience of time, I've accelerated and warped space-time so much that I have a completely different experience of time than everybody else. Now, if you're watching me travel to that star and back, and you're just sitting on Earth, so relatively to the speed of light, you're going much, much, much slower than me, you're going to actually see me go, and it take over 10 years. Because I'm not quite going the speed of light, and it's going to take all that time for light to travel to the star and all that time for light to travel back. And so 10 years or more will have passed for you, while only a few minutes have passed for me. Now, that's one of the most basic of Einstein's thought equations, dealing with dilation and time and relativity. And it's the one that most people are very familiar with. But what we're not generally, or most people are not as familiar with, is that acceleration is something that occurs that literally warps the space-time fabric itself. So acceleration and gravity are actually the same thing. Einstein has another thought experiment that when you go up in an elevator and you experience the push of the elevator going down because it's accelerating to go up, that field of force, the experience of that, is indistinguishable from gravity. And here's the reason why. It's because when you speed up in a car, you speed up in an airplane, you're literally pushing your way through this crystalline energy lattice. You're pushing through space-time. And so this is why it takes a lot to speed up. It takes a lot to move your arm fast. And the more fast you go, the more G-force you experience, the more gravitational force you feel pressing against you, because you're literally creating gravity through acceleration. And what happens is that when you send a rocket into space, if we were going to try to get to, another star system 5 light years away, we're going to accelerate and accelerate and accelerate and accelerate, and we keep accelerating. And the more we accelerate, the more we're pushing through that fabric of space, the more tension is created. And the greater and greater that tension is, the more difficult it is to accelerate, to the point where as we approach the speed of light, it becomes infinitely difficult to go faster. This is the general thinking of physicists that have followed Einstein's work and looked at this, and they say, well, it's impossible to go the speed of light because it takes infinite energy to accelerate to that speed, right? And so this is really fascinating too when we look at something like the proton, which Nassim Haramein postulates, and through his paper equated that the proton should be spinning at the speed of light. Now, in his mind, the whole thing is moving at the speed of light. But when I heard that, I knew that there was an issue with that. Because if the whole thing was spinning at the speed of light, it would have no mass at all. Because once you hit light speed, the mass, time dilation, etc., all goes to zero. So an object going at light speed has infinite mass or zero mass, and they're actually the same thing. And so photons, which are calculated to have no mass, travel at the speed of light, and there's an equality between the nature of their movement at light speed and their mass being zero. So if a proton in its fullness was spinning at the speed of light, mass is going to equal zero. But that's not what we see, is it? Because all matter and all the different things that we witness, the construction of the objects that we engage with all the time, is based on the mass of the proton. And the masses of protons combining together in the nuclei of atoms, and those giving rise to different molecular structures and all of the different objects that we see and witness. So I knew there was a problem with this idea that the whole proton is spinning at the speed of light. Because as soon as I began to assess that, I realized, well, maybe it's moving at the speed of light at the equator. And if it is, and if the proton is actually this highly geodesic crystalline structure, just like the rest of space-time, and in fact, it should be more crystalline, even more solid than the rest of space-time, because after all, we experience protons as pretty solid, whereas we experience the empty space between protons as a lot more malleable, right? So the speed as this crystal is spinning would have to fall off. In other words, it'd have to decrease as you move from the equator towards the poles. And in the course, I actually do some calculations on this, and I show you a table, and we get in depth into the nature of this speed fall off. And I show you that actually, if the speed fall off is static all the way up the side, all the way to the pole, then eventually at the pole, it's not even turning or moving, it's just rotating in place, and so its speed is actually zero. However, because there's also a pull into the proton and a radiation out of the proton, just like there is around every other black hole, every other singularity structure in the universe, and of course we'll talk about singularities, black holes, and the nature of this inward flow and outward flow as well throughout the course, it's most likely that as it's spinning and goes up and is slowing down, getting slower to match the light speed movement of the further distance at the edge of the equator horizon, there's a point where the pull inward overcomes the centripetal force and the spin force, and that the PSU in the polar regions would actually cascade into the proton, which actually validates in an even deeper level this sort of toroidal model of the proton itself. And so while the whole thing is mostly spherical, it's possible that there's little dimples at these points and these vortices at the top and the bottom of the proton. And one of the things that I'll show you as we go into the course is that if we look at protons in this way, it suddenly gives us a much deeper explanation for what the most solid bonds that a proton can make are. Because, for example, we have two different types of elements or atoms that we say have two nucleons. In other words, what we think of as either two protons or a proton and a neutron. And what I'll show you in the course is that when protons stack on each other and spin together, they conserve force. They conserve spin because they're spinning together. And because they're spinning together, that spin charge is conserved and the amount of charge that they propagate is conserved. And so when we see two protons spinning together in total equilibrium, what we look at and what we see as far as its charge is about half of what two protons independently spinning should create. And because of this charge conservation, I propose that neutrons are actually just protons in a nucleus that are conserving charge with the spin of other protons. And so this really gives us some powerful insights into the nature of atoms themselves and lets us start to actually build the structure of nucleons in the geometry in the core of atoms and actually get to know how all of these little spinning spheres are pulling and torsioning the surrounding field of space-time, creating different kinds of electron fields, and then, of course, different kinds of elements and different kinds of molecules. So that's a really fun part that we're going to dive into deeply. But I'm also going to show you that the other possibility for bonding of two protons could happen right at the equator. And when you have two protons bonded at the equator, it would be extremely unstable because at the equator, they're traveling at the speed of light. And so there's no mass energy effect pulling them together. There is some mass energy effect, but only because as you leave the equator, the speed drops slightly below light speed. And as the speed drops below light speed, suddenly now you're dealing with mass dilation and the pull and et cetera. The tension of the mass energy effect is now there. And so there is some pull, but it's not very stable. And it also requires that the two spheres are spinning in opposite directions. So through the course, I'm going to talk to you a little bit more about equatorial spin and counter-rotating spin in nucleons, meaning protons, and polar spin, where they're spinning together. And we're also going to look at hemispheric spin. And hemispheric spin is where the points of curvature that exist in the ring around the upper hemisphere of the proton, not to be confused with the pole, but around the upper hemisphere and around the lower hemisphere of the proton and the lower pole, those hemispheric areas are also prime places for protons to bond together. Now, of course, when they do this, they also will have to counter-rotate. Because if you have a circle on a sphere rotating this way and it's coming in contact with another, that other one has to go the opposite direction in order to spin with it. If it goes the same direction, like this, then by the time it gets to that same point, boom, they clash. They don't move together. And so you can think of these as like little spindling gears moving with each other, counter-rotating. And this gives us a really classical way that's both geometric, that's elementary to an extent, to actually look at these dynamics. One of the things that Einstein said is that when he looks at a really difficult problem, if the answer is not simple, it's probably not correct. And so as we look at the field of unified physics and begin to apply the most basic things that space-time is this crystalline structure, that this crystalline structure curves simply through the radiation of one of the points in the hexagonal lattice, allowing it to curve, and that it can curve even sharper or more dense, but only if another point is radiated out, and the compression of that curvature, which goes to octahedral, would be highly, highly extreme. But that all it takes is radiation for there to be compression. Yin and yang, one and the other are the same. That things in the universe compress together when they're shining, and they also shine when they're compressing. As we squeeze a crystal and release light or electromagnetism out of it, so we see these basic properties of space-time. And that space-time is made of this sort of field which has oriented itself around these co-spinning PSU, spherical light crystals. And these spherical light crystals are the ultimate example of curvature and high energy, but in a state of great balance and equilibrium. And then when we look at these little balls spinning together, we start to see how they construct these atomic structures. And then when we look at the potential area of electron fields and we start to see the probability vectors of where electrons should be, we start to notice that they're occurring at areas that would be pulled by the tension of these core nucleons. And so through this, we start to have a more unified perspective of not just space-time, but of the nucleus of atoms and of molecules and the way that each of these generate each other. Now, along the way, I had another pretty big breakthrough, and that breakthrough came from this simple understanding that a neutron is actually just a proton that's conserving spin in a nucleus. Now, one of the four fundamental forces, one that's not been written about in unified physics at all, is the weak nuclear force. And the weak nuclear force is a force that's used to describe how a neutron decays back into a proton when it's freed from a nucleus. As some of you know that have been a part of our, long journeys together in the Resonance Academy and sat through countless talks by myself or Nassim or William or others, you've probably heard the idea that neutrons are not stable and that they decay into protons, and so they must not be fundamental. And Nassim has proposed this for a long time. But why does a neutron become a proton? And what are the W and Z bosons that are supposedly radiated off? And what is this release of an electron and an antineutrino? And what goes on in this decay process? Because as neutrons decay to protons, guess what? That's exactly the mechanism that we use for carbon dating. And if we don't understand the fundamental physics of the mechanism that we use to carbon date objects, then how can we assume that we have a very, very clear assessment of the timeline of ancient structures all around the world? Well, I propose in this course and also in a forthcoming paper that I'm working on right now and that Robert is contributing to and Talal may be contributing to as well, that this process of nuclear decay, the weak force itself, and the decay of carbon-14 into nitrogen-14 atoms, which is what we use for carbon dating, is actually all based on an orientation in the nucleus of atoms, where you have a neutron that is in a state of conservation of spin with the other protons in the atom, and its geometric position changes, allowing it to spin on its own and developing its own torsion field, and so it acts like a proton. And when that happens, there is a release of energy. And what we can see happening is that if we only had two, and the two were spinning together, they're conserving charge and they have a shared effect on the surrounding field. As soon as one of those splits off, now they both have an independent effect on the surrounding field. So now there's got to be this extra energy that's moved by that separation. Space-time is going to move more with each of them independently spinning than it did with them together. And that additional energy spin is the extra electron, and as I'll show you in the course, the other force particles that are discussed. And in my weak nuclear force paper, I'll unpack the W and Z bosons further, but that's a little bit beyond the scope of this particular course. So within this, I'm going to give you as much foundation as possible to really glean the quantum geometric dynamics of space and space-time itself. And then from this, as we go through this whole journey and go through all of these different layers of understanding the tensegrity in space-time, the nature of chromodynamics, the nature of the vector equilibrium, where and how space-time curvature occurs, radiation and spin, the dynamics of proton spin, the dynamics of nuclear geometry and the different elements that can arise from that. Eventually, we kind of close the course through a revisiting of these fundamental geometries that give rise to these different principles and dynamics that we see throughout the course. And we look at just a little bit how each one of them is connected to all of these different philosophies and forms of thought around the planet. And through this, we began to reveal a little bit more that perhaps a lot of our spiritual traditions and religious traditions on the planet are not isolated to some kind of higher dimensional experience that's not connected to the physics of our reality, but that they may be actually tapping into and gleaning deeper aspects of the reality that we inhabit, and that consciousness and space-time may be as above, so below, and such that we are literally are experiencing ourselves as the universe unfolding. And as we get to know the geometries within us, so do we better understand the geometries outside of us and the nature of space and time. So, all right, that's my rant for this course. I will happily take a few questions here. I'm going to look through here and see what you guys are saying. Greetings to Quebec, Canada, and Connecticut. Yeah, so let's dive in here a little bit further and just take a few of these questions in the Q&A. And thank you guys so much for being here with me. I hope you join the course. I hope you dive in. It's going to be really fun. Please share it with your friends too. By the way, I know I can get a little technical in my rants, but a lot of the course is written with visuals. And the reason I did that is so that you don't just hear me blurring through stuff and maybe you couldn't keep up in your notes, which I hope you did take notes. But that you can actually read and comprehend and understand and revisit and read again if you need to really take your time. And I also want you to know that I'm a big fan of metaphor. And so I don't just discuss things from highly technical mathematical aspects. I often will give you references for that and point you to things that you can look at if that's your core interest. But I really like to help you build understanding. And so that means, you know, taking these concepts and breaking them down in a way that lets you kind of take it bite size and take it one step at a time so that you have a really full perspective framework of the ideas that I'm sharing here. So Nathan Navrete says, does each organ, endocrine, and body part have a specific geometry? Good question. Probably a little bit more suited for a biology course. And William could probably answer this question better than me. However, I can say that there are very specific geometries to the muscular systems and the tissue structures that make up our different organs. In fact, most of the cells in our bodies are very, very similar. But the way the cells combine to form different tissues align in different geometries. And those different geometries give rise to the effect or purpose of the structure of that tissue. So heart tissue, for example, has very different structure than liver tissue, which has a different structure from intestinal tissue, which has a different structure from skin tissue. And each one of the different types of tissue structures embody a sort of different event horizon, if you will, a different boundary condition. And the different kinds of boundary conditions exhibit charge in different ways. It's really cool when you look at the muscular geometry of the heart, because when you actually unwind the muscular geometry of the heart, you actually have two counter-rotating cones of muscle. And these counter-rotating cones of muscle slide and overlap on each other. And because of this, this dual cone structure, there is actually a huge amount of research into the fact that health in the heart happens not from the heart just being massive and open and not just tiny and closed, but being right in the right balance where these structures can interact just right. And the crossing of these cellular structures in the tissues of the heart, we can also see as literally an electromagnetic generator. So the friction and the flow is literally generating electromagnetism, which is one of the reasons why the heart is this massive generator we can pick up from up to 50 yards away at times with sensitive instruments. And so all of our different organs do have different geometries. Are they specific to one or another, specific Platonic geometry or something like that? I wouldn't say that. But I would say that there are geometries that regulate our glands and that regulate the heart and other organs. And I think there's a lot of work still to be done to fully understand and unpack these things. Some of the work done around the heart that I appreciate the most is by a gentleman named Mark Chester. And he created this geometric structure he calls the chestahedron. And interestingly enough, it's the geometry in your chest. It's the geometry of the heart and represents the kind of bell-like conic structure of the muscles of the heart. So I'll have to have you pass that one to William in the next faculty Q&A. I'm sure he would love to answer that question. And thanks for being here, Nathan. All right, let's see. Andrea asks, will the webinar be available to view later? If so, where? It looks like I may have already missed you, Andrea, but yes, this webinar will be available on the course landing page for registration, and it'll be available there as an intro to anybody who wants to take this course at any time. So you can send your friends to the quantum geometry course page, which I think has been posted in the chat a couple times, and I'll make sure to do that at the end of the call as well. And you can have them watch this if they're interested in exploring some of these ideas. All right, let's see. A little bit of a question about the template. There's a specific mathematics. There's a specific type of mathematics that someone talked about relating to the fabric or quantum. What's that specific type called? So this question's from Leah Otto, and it's asking about the type of mathematics that is used to explore the sort of structure and dimensionality of space. Now, there's actually a few different kinds of mathematical approaches to the structure of space. By just looking at sort of the dimensionality of directionality and vectors in space and vectors in time, we use mathematics that usually uses the Minkowski space projection, which is a sort of four-dimensional approach to understanding distance and vectors in space and time. If we're going down all the way to sort of Planck scale structures, there's actually very little mathematics that does that work, but Lee Smolin produced some early mathematics on the discrete structure of space, and it provides to some extent a decent look at the way that space-time units may interact with each other. But a much better mathematical formula for studying the interaction of the fundamental structures of space is in Quantum Gravity and the Holographic Mass, which is a paper by Nassim Haramein with assistance from a gentleman named Orion Bard and others. And those mathematics help us to sort of count the discrete structures in space and look at their intersections. The paper's not perfect. If you pass it to any physicist, some of the things that Nassim describes are a little bit different from what you see in the paper. For one example, when he's counting the PSU inside of the structure of the proton, he just counts them edge to edge. So the number of PSU in the diameter of the proton or radius of the proton are counted edge to edge, whereas we actually see and look at the PSU as being in intersection, more like the structure of the flower of life itself. And that the part of the tensegrity and the embedding of the PSU is what connects them and connects the pulse waves through space. But even though he was only accounting for every other PSU, and that's the number that's counted, the mathematics works out to be exactly the same. Because if you have end-to-end PSU or circles, cut in a line, and you've got another PSU in every in-between space, the distance of Planck lengths as far as the diameter of one PSU, the distance in Planck lengths actually works out to be exactly the same. So there are things that are not explained that well, and perhaps less poorly translated, let's just say. But with some help from those of us that are faculty and that have really deep dived into these different things, we're going to help you understand them. And any physics paper can be a real challenge to read. So I'm doing my best to kind of flesh out my weak force paper a little bit more to make it not only accessible to physicists and mathematicians, but also to our students in this academy, because I deeply care about this learning process. Thank you, Leah, so much for your question. It's the way, and why graphene has properties. So Andrea also asked, is this why graphene has its properties? And graphene, in case you guys don't know, is a lattice of carbon atoms that is hexagonal. And so graphene is like a hexagonal lattice, but without center points in the hexagon. So they're open hexagons, which is actually identical to what we see when we look at honeycomb, for example. And graphene is extremely strong, extremely light, and has superconducting properties. So it's able to superconduct electricity through being in this state of hexagonal equilibrium. Well, isn't that fascinating? Because we look at space-time as this superconducting, potentially superfluidic structure. There's all these papers looking at these properties of space, but few have come to acknowledge that perhaps one of the reasons why it has those properties is because it's a highly energetic structure in total tensegrity with itself. In other words, it's all in equilibrium. In other words, mostly equilibrium. And it allows energy to pulse and travel through it in a superconducting like format, while also retaining its structure and of course through its curvature, creating gravitation and flow fields which influence light and other matter and etc. So yes, that is exactly why graphene has those properties. There's something about the hexagonal geometry itself which contains this equilibrium-like structure that has tensegrity properties that I think it mirrors the fabric of space. And so by doing so, it leverages some of the same properties and effects. Hey, Charlie, good to see you too. Charlie Peck says, do you think the answer to some of these equations are built into the structure of the Great Pyramid? Charlie, after hanging out with Alan Green for a long time, I can tell you that there are probably very few things that are not in the structure of the Great Pyramid. It's absolutely amazing that the basic proportions of the Great Pyramid itself give rise to all of these different equations and dynamics that show us different mathematical constants, that show us the Planck length, that show us the relationship between the foot and the meter and the cubit, all units of measurement. And so the question is, did they intentionally embed all mathematics and the whole universal thing into the pyramid? I think the answer is that it didn't matter if they were intending to embed all of the things, but that the Great Pyramid actually represents and is a Rosetta Stone, in a sense, of mathematics and of higher level thinking. And so it's built so that its proportions between the different aspects of the structure embody a whole series of universal principles, which in turn reveal to us all of these different facets in space-time. So for those of you that are coming with me to Egypt next week, I'm so excited to be there with you and Alan and Robert, and Robin Davis is joining us, an amazing Templar oracle who's on our team and a brilliant woman. Jamie Janover, who I believe is on the call with us, will be there as well and sharing with you some of his insights. And it's going to be an absolutely amazing adventure. We're going to be doing a virtual sharing of our adventures there. So for those of you that want to kind of follow along with us, you can join in the virtual series, and we'll be actually broadcasting and uploading stuff from the talks that we do there and from a lot of the different sites. You might not see me doing talks on the virtual broadcast because I'm mostly going to be doing deep dives around the fire at night, and we're probably not going to record those. But I'll be there on the sites and perhaps sharing with you bits here and there about the different hieroglyphics, and showing you some of the deeper knowledge and wisdom encoded in Egypt. So that's coming up literally next week. So we're opening this course. We're going to dive into quantum geometry, and then I'm going to go to Egypt, and I'm going to be showing how the quantum geometry is embedded in these structures that I believe in many cases are much, much older than the archaeologists have taught us. So it looks like I am running out of time. Let me just see. I might take one more question here. Let's see. So Zeely asks, what is squeezing space-time to generate the piezoelectric effect? If we know the vacuum is energized and we know roughly probably the geometric shape of it, how can we utilize this information for something useful, like acquisition and use of zero-point energy for the betterment of humanity? Great question, Zeely. And in fact, that is the standing question and the standing field of research that those of us that are part of this academy and the foundation are deeply dedicated to. And there are projects actively going on exploring some of the different aspects of this. Some are further along than others, and some have produced amazing outputs. The Art Crystal is an output of one of those experiments. But a lot of our work in that space is really about understanding this tensegrity structure and understanding how it changes when it's spinning and rotating. What happens if we spin space? Because spinning space is accelerating it constantly in a new direction. So it's both creating the pressure internally of space against space, in other words, squeezing it just right, and also following the sort of biomimicry of the natural condition of space-time in its own production of energy. As we understand the proton, it's really critical because after all, protons are the objects that last longer than anything else that we know of in the universe. The half-life of a proton is estimated to be 4 times the lifetime of our entire universe from the beginning to now. Just think about that for a second. 4 times the lifetime of our existing universe is what we estimate the half-life of a proton to be before it will decay. And then what does it decay into? We don't know because we've never seen a proton decay. And how we even come up with the idea that we could estimate that it would last 4 times the lifetime of the universe, I think is a pretty big leap, because we don't see protons decay. They don't. The only time protons come apart is when we blast them apart at nearly the speed of light in accelerators. And when we blast them apart, they shatter into little pieces, and these little chunks of co-spinning PSU spin off and then dissolve right back into the structure of space-time, right back into the tensegrity field, pressed right back into equilibrium, and are gone. And so, the proton is sort of the ultimate example of a free energy device. It's the ultimate example of something that's literally spinning at the speed of light at its horizon. It's torsioning space-time. It's generating electricity as electron fields are spinning around it. It's allowing the bonding of molecules together. It's allowing all the properties of everything that we see around us to come into being, not to mention the spinning of planets, the gravitational field and spin of stars, and all of that is just based on space-time co-moving together in the right geometry. So I think the most promising approaches to doing this is about leveraging geometry and leveraging the co-moving properties of that geometry and understanding how space itself likes to spin to generate energy, and just letting it do that, just helping it do that a little bit better. And maybe not better, but in a way that we can then apply the field of that force to space itself. There is so much amazing research being done on getting energy out of thin air, so to speak. And there was just an article I was looking at earlier today where guys have built biological nanotubes, and the nanotubes literally just vibrate from the movement of the molecules of the air around them and capture electricity. And they're looking at putting this into paint and putting this into the surface of different kinds of objects and materials to capture electricity, putting it on your cell phone so that you never have to charge it again. Space-time is already so ripe and full of energy. The sun pours it down upon this planet, giving life all the time. The moon is torsioning the gravitational field of the Earth and pulling the tides around. I mean, there's so much energy all around us. And it's time that we learned how to apply the basic understandings of these fields in physics and our relationship with space, and stop burning dinosaur blood and causing explosions in one thing, which is damaging and destroying and creating smoke and all of these things just to propel ourselves somewhere else. And just like our rockets, it's time for us to stop pushing our way through the fabric, blasting our way through space-time by exploding bombs behind us, and instead start looking at how does a proton spin at the speed of light? And how is an envelope created around a proton that lets it float around, even though it's extremely massive black hole around a singularity, it floats in the air, the hydrogen atoms cruising around, hardly even influenced by the gravity of the Earth. And so it's a deeper exploration of our relationship with space and time that will show us the keys to the technology in the future. And I think a lot of the biggest breakthroughs we need are encoded by our own consciousness's capacity to understand our responsibility and our relationship with space and time itself. So I hope through this course, you'll get a deeper dive into the nature of the quantum geometry of space, its relationship to consciousness, and how we can be more responsible ambassadors of the information that unlocks the secrets and the keys to the magic of the universe, and how and what we can create through application of that magic to changing our lives. So, all right. Thank you guys so much. Please enjoy the course. There will be links put in the chat. I think there already were. And David or Jamie, if you're still there and you want to post those links again, that would be super awesome. I'd love to have it. And if you want to review this video again or share it with your friends, as soon as we can get it posted on the course landing page, you'll be able to share it with people there, and they can watch it. You can watch it again and use it as a refresher. And the course itself, I think, will give you all the juice you need to get to the next phase. And for those of you joining us for the virtual adventure through Egypt, I look forward to seeing you in those spaces. And those of you coming in person, it'll be an honor and pleasure to be on this adventure with you through these ancient sites. Thank you guys again so much. And blessings, and I look forward to seeing you all in the course. Thank you, aloha, and good night.